Thank you, Susan. So today we're going to talk about machine learning, and we're going to talk about it specifically with respect to how it might successfully be applied to software effort estimation. Not a hugely well-studied thing. There have been studies on this, but I think it's worth talking about. So here I am. So the agenda for today, just an introduction why I think this is an interesting topic. Talk a little bit about software effort estimation. And I imagine that most of the audience is comprised of people that have software expertise. And you probably all know that estimating the effort for a software project is sometimes problematic. Then we're going to talk about artificial intelligence and machine learning. So what is AI? And what is machine learning, and how are they different, and how are they combined? And I'm going to talk about some interesting machine learning techniques, not all of them, ones that I have delved into. And then I'm going to sort of talk about an exercise that I did applying machine learning to a particular software effort data set. And I'll tell you up front that my results were not hugely successful, but I learned a lot, and I think there's a lot to learn from taking a singular data set and refusing to make modifications to it other than the ones that are necessary to multiple techniques, just to see how they rack and stack against each other. There's more work to be done in this area, but I think it's a good first step. I hope you agree. So in 2017, Project Management Institute, they did a survey and determined that 69% of software projects successfully met their original goals and business intent of the project. In other words, they managed to do the project in the estimated time and managed to relatively make the consumers of the project happy. 43% did not finish within their initial budgets. 48% were delivered late. 15% failed completely. And the study said due to inaccurate effort estimation, and I like to caveat that with saying inaccurate estimation, most likely not just because the estimate was bad, but because the projection of what the project was supposed to accomplish was probably understated as well. So software effort data, it's available, but it's noisy and it's hard to interpret. We do at Price, at Unison, we do hardware estimating models and software estimating models. And the thing about hardware is once it's done, it's pretty easy to figure out what the unit production cost for a tank is, or for an aircraft. It's a lot harder to get precise information on what the software development costs were for that tank, or for that piece of avionics, or for that aircraft. I think, and I believe, even though I haven't had a whole lot of success with this particular study, but I think that machine learning might help provide a unique approach to interpreting software effort data. And that's what I'm here to talk about. So first, let me say a little bit about software effort estimation. It is the process of predicting a realistic estimate, a realistic value for how much effort is going to be required to develop a software project. It might also include, I talk about effort more than I talk about hours, because as a both hardware and software estimator, hardware, you definitely have hours and you have material. Software projects are mostly just hours. So I talk about hours more than I talk about currency. But a software estimation should include hours. Those hours should be converted to currency if currency is an issue. And they should also include schedule information. I contend that it's more complicated than hardware estimation. And I don't even say this tongue-in-cheek because it's true, but although software development has been around for a really long time, compared to hardware, it's a relatively immature discipline. And it's just also harder to capture and interpret and analyze software data. As I mentioned earlier, I can go on Wikipedia and I can get the unit production cost for any jet fighter, any tank. It might not be 100% accurate because I'm getting it from Wikipedia, but I can go to Wikipedia. I can go to different journals maintained by the Department of Defense and or their contractors. Nobody prints on Wikipedia how much the software for the F-15 was. It's just harder because it's, first of all, a development cost, not a production cost. So it's harder to represent. And because a lot goes into figuring out, software data includes, and I'll just talk about effort for this particular conversation. You want to know how many hours it took to build the avionics for the F-15 or the F-18, whatever. So you go back and look at time cards. You talk to the project manager. You talk to the systems engineer. And the problem is that oftentimes those numbers are wrong, either because the project is billable and it took more hours than you're going to bill for whatever reasons, or people don't want to admit that it took them too long or too short to do something that they said they could do in 300 hours. So there is some creativity in the collection of software effort data, and it's hard to capture. And then, we have software size and productivity, also hard things to capture and institutionalize. So there's several different ways that people have attempted through time to perform a software effort estimate. Three main categories: algorithmic, so using statistics and math. So my product, as well as some of our competing products, Kokomo, which is open source and widely used in industry and in universities. Function point analysis. There's various algorithmic ways, non-algorithmic, based on some sort of analytical assessment, interpretations of historical data. So, we have expert judgment, which has always been an important way, analogy, planning poker, doing some sort of a Delphi, and just a sort of bottoms-up work breakdown structure. What are all the pieces and how much does each one of those cost? And, what's the overhead to get them all working together? And more recently, we have machine learning techniques. Although, to be fair, the statistical techniques are also considered machine learning. But newer ones, such as neural networks, the KNearest Neighbor, regression analysis, which goes back to the statistical, support vector machines, random forest, decision trees, etc. So these are all methods that have been used historically to come up with software effort estimations. So just a little bit about AI. Machine learning is a sub-practice of artificial intelligence. So in general, artificial intelligence, it combines computers and machines to attempt to replicate problem-solving and decision-making capabilities of the human mind. It's built on the hypothesis that mechanizing thought is possible, which is both fascinating and a little scary. There are subsets of AI which include reasoning. So a computer will make inferences based on data and fill in the blanks where data is incomplete. So unlike a pure logistical regression, there's some interpretation of the data and some extrapolation. Natural language processing, which trains computers to understand both written and human speech. So, if you have Siri, or if you talk to your iPhone and tell it to call your husband or wife, and it does, that's natural language processing in action. And there's a planning function of artificial intelligence. It allows computers to build a plan to accomplish a goal. So, assembly line kind of stuff, the robotics. And then machine learning, which machine learning is fascinating. It allows a computer to ingest data and use that data to make both classifications and predictions based on what it learns from that data. It's not a new concept. It's been in practice in people's minds and thoughts since 1950s. Several instances, Arthur Samuels, who was a researcher at IBM, he developed a program for playing checkers. So a computer beating a person at, or attempting at least to beat a person at playing checkers. And then Alan Turing, who published his book, Computing Machinery and Intelligence. So those were a couple instances of early attempts to talk to industry about artificial intelligence. And definitely the market for both artificial intelligence and its subset, machine learning, they have ebbed and flowed over time. Sometimes they were very popular when they were first introduced, and people began to realize that, okay, so this computer can beat me in checkers, but I can't balance my checkbook or figure out what I should do next in my career. So it's ebbed and flowed. Over time, it has become increasingly real because of technology. Okay, modern processors are more powerful and increasingly dense. And the cost of storing and managing large amounts of data has absolutely lowered dramatically. And due to increased processor speeds, lower cost of storage, and just increases in technology, storage innovations have made it faster to analyze really, really large sets of data. Add to this the fact more commercial data sets are available to support advanced analytics. So there are data sets that one can purchase. But there's also, if you're familiar with big data, and if you think about Kaggle, Kaggle.com, it's a website that basically publishes open source data sets to help people that want to get good at machine learning through applications to very large data sets. The IEEE, the Institute for Electrical and Electronic Engineers, has a data port where they collect data sets that are available to their members. Once again, open source data sets, not 100% open source because you have to be a member, but data sets that anyone that is a member can use, once again, to advance their machine learning capability, as well as and their data science capability, as well as to advance studies that people want to do around things that the IEEE cares about. And there are other data. There's data.world, I think it is, also provides open source data sets to people who are willing to register and get emails from them regularly. So there's a lot more opportunities for people to have access to large data sets that allow them to become proficient in machine learning, and B, have access to data sets that might allow them to make interesting discoveries. Also, the algorithms for machine learning are available through open source communities. There's Python. I'm not endorsing products. I'm just mentioning ones that I'm familiar with. So R and the R Studio. R and Python are two very popular languages for accomplishing machine learning tasks. There are Anaconda and RStudio are both open source. There is also RapidMiner, which has an open source version of their tool that has algorithms for many machine learning operations. And things like Power BI have made visualization a more consumable thing. And people, I personally am not a hugely great visual learner, but many people are, and visualization is a huge benefit when you're trying to figure out how to understand your data sets. And it is a fact that machine learning models the accuracy of the results that you'll get out of a machine learning model are going to increase significantly if you are able to train them on a big data set. So the way machine learning works is you have a large data set, you supply it with 75% of the data to train it, and then you look at the other 25% and see how well you trained it. So the bigger your data set, the more likely you are to be successful with machine learning projects, in theory at least. A problem, I'm here to talk about machine learning. I'm also here to talk about software estimation. And sometimes the fact that that we don't have huge data sets for software estimation, so it's sometimes hampered by the lack of big data, because it's harder to train the machine learning algorithms on smaller data sets. But sometimes it's necessary, and I don't think that we should abandon the concept that machine learning is going to help us with software estimation just because we have small data sets, smaller data sets. So what is machine learning? It's, as I said, a form of artificial intelligence where, rather than the programmer programming algorithm, the programmer or the data scientist feeds data to the machine learning algorithm, and the machine learning algorithm gets trained by that data. So, if you're talking classification, let's say you're trying to make a very simple instance, the difference between a cat and a dog. So you feed your machine learning system a ton of pictures of cats labeled cat, and a ton of pictures of dog labeled dog. And it learns the differences between a dog and a cat. And then you feed it the rest of your ton of pictures of cats and dogs, and its job is to figure out which are cats and which are dogs. So that's classification. If you talk about software estimation, and let's very simply, once again, feed it a bunch of function point counts with corresponding effort for enhancement projects, you feed it a ton of that data. It learns from that data how best to infer effort from number of function points. And then the part of your data set that you kept aside, you feed that back and determine how well it has actually learned and how good it is at predicting effort from size. So algorithms ingest training data. That would be pictures of cats and dogs. They build models based on that data, and then they use these models to predict outcomes based on the training data against the test data that's put aside. There are categories of machine learning: supervised learning, which I just talked about. The data has labels, and the machine is able to learn from the labels how the data is classified. So which are the cats and which are the dogs. Unsupervised learning: the data is unlabeled, and the machine needs to determine classifications. And oftentimes, this unsupervised method of learning is used as a precursor, not a precursing, sorry, to supervised learning, as it creates labels. So sometimes one uses unsupervised learning to take a great big data set that they're not sure how to label, asks the machine via unsupervised learning to label that data, and then using the labels provided, then applies it to a more supervised learning algorithm. Reinforcement learning: this is what robots do, learning through trial and error. So a robot that's learning how to climb stairs is going to have missteps, and there will be correction, and then over time the robot will get better at climbing stairs. And then the most fascinating part of machine learning, and the part that I know the least about, is neural networks and deep learning, where a machine is actually expected to learn based on how a human brain works. And I think it's fascinating. Neural networks, you have an input, you have a layer, a hidden layer, and you have an output. And the computer translates from the input through the hidden layer to the output to come up with conclusions. And as I said, this is the part of machine learning that I'm still in the learning a lot about, but I think it's fascinating, and I think there's a lot of promise in that. I don't think that machines will ever be able to emulate how the human brain works 100% or precisely, but I think it's a pretty exciting thing to think about. And I think as a software person, it's it's sort of a great goal for data science and machine learning and software development to think that someday we could make that happen. So machine learning algorithms are different. Traditional algorithms are implemented by programmers. With machine learning, the data itself is used to create and improve the algorithms. And some of the technologies that have enabled the renaissance of machine learning include data virtualization, the ability to do parallel processing. So think about big data, think about the fact that there's massive amounts of data, and think about the fact that the laptop on your desk is not going to be able to solve a lot of problems in a short time. But if you have access to, through the cloud, or through a server bank or whatever, if you have access to multiple processors that can all help solve the problem in parallel. The fact that we have distributed file systems, that we can load huge amounts of data into memory for real-time processing, the fact that we can containerize data, and then the existence of microservices, things that are that are able to, small scale little things that happen fast and quickly and apply to a lot of data. One of the concerns that I hear when I talk to people about machine learning, that it might be a replacement for knowledge workers. It won't be a replacement for knowledge workers. Machine learning is going to increasingly take over some of the mundane and repetitive tasks that knowledge workers do on a regular basis. But I believe that it should also be opening up these new opportunities for more interesting and creative tasks. If we can get the computers to do all the boring stuff that we have to do, I think that opens up opportunities for us to do more interesting stuff. I also think the task of getting the computers to a place where they can do all the boring stuff that we don't really want to do is in and of itself an interesting and creative task. So I don't think that machine learning is going to replace all the knowledge workers on the planet. I think that it will replace some people, or it might not replace them. It might free people up to do more interesting and creative things. There are several avenues of machine learning focus, but the one that I've studied and the one that seems to be currently the most popular and the most well used is the Bayesian approach, which is based on statistics. Certainly from my perspective, and my study was focused on software effort estimation, that it was most relevant to the study that I did, so that's what I focused on. But also, statistics is a well-established technology, and it's well understood, and most people that are likely to pursue machine learning opportunities, machine learning projects, are going to be more comfortable with Bayesian approaches and based on statistics than otherworldly approaches. Not to say that any of them are bad, they're just not as well fleshed out and not as well understood. And the other thing about machine learning, and it is a huge issue in the market that I live in. It has a real black box kind of an aura around it. Many times when you use the technology, whether you're using RStudio, whether you're using RapidMiner, you have a training set, you have a test set. The training set builds a model. The model is applied against the test set. You get statistics from that, but you don't have an equation to show the consumer of the estimate necessarily. If you're doing something like random forest or neural networks or something, you don't have the equation. And I find that, and I believe that that is a barrier to being successful. I don't think it's an unsurmountable barrier. I think it's a barrier. Certainly in the market where I live right now, it's a barrier. But I think that as a community, the software community should be pursuing machine learning solutions and pursuing ways to make machine learning solutions consumable by the people that we need to give our estimates to, in a way that, while they might not see, effort equals size raised to a power times a constant, that they're comfortable with the results. Secret to machine learning is generalization. And to achieve this generalization, the learner algorithm, it relies on representation. So proper models that understand which features to use for the learning process. So you could have a very large data set. We'll talk about big data in a minute. You could have a lot of data. And some of the features, so, in machine learning parlance, data set has examples. So those are the rows of each instance of a data point, and then features, and those are the columns. Those are the attributes. In machine learning, we call them examples and features. In Excel, we call them rows and columns. So representation, you want to have a model that figures out which are the best features to use for the learning process. You want to have functions that score the model to determine which of the many models that might come out of a machine learning algorithm actually provides maximizes success. And then over time, because machine learning algorithms learn from data, and data is constantly being collected, you want optimization. You want to make sure that you have the best model going forward based on all the data that you have today. And when today comes next week, you want to have the best model going forward based on all the data you have on that today. So big data, just a little bit about big data. So in order for you to have your computer learn from your data, you need a lot of data. You need to have enough data that your algorithms are able to recognize patterns and to be able to use those patterns to make predictions. 4 things that are important about big data. And, big data doesn't mean that you just have a lot of data. It does mean that you have a lot of data, but it also, it's broader than that. It is voluminous. Your big data sources have lots and lots of examples in them, and potentially lots of features. But the use of big data requires velocity. You need to be able to move that data at a very fast speed, which is what velocity means. So for example, you're collecting big data from sensors on street corners. And in order for that data to be useful, it has to go from the street corner. Okay, if we're looking at traffic lights, so we're looking at crimes, we're looking for potential crimes. Figuring it out next week that there was a sketchy character walking down the street doesn't do anybody any good. You need to figure it out in real time or near real time. So there needs to be a velocity perspective. The data needs to be able to handle a variety of data from a variety of data sources. So big data is not just an Excel spreadsheet with rows and columns. It's a collection of data from sensors, data from websites, data from Facebook, data from multiple social media venues that needs to be coalesced. It needs to be the computer needs to figure out what's important, what's not important. It needs to figure out how to handle the social media aspect, which is in free form, versus the sensor data, which is pretty tabular. And you need to trust it, veracity, so that the big data needs to come from sources that truly represent the truth. So if you're able to combine big data, once again, I'll talk a little bit more about software estimation. We don't have big data. We don't have a lot of, we don't necessarily need all of these characteristics of big data, but I think they're an interesting aspect of machine learning. But if you can combine big data, or even with the software estimation perspective, medium-sized data, with statistics, you can create an environment where a machine can figure out the probability of a given event, meaning that your 2,000 function point software project will get done in 12,000 hours. Please don't quote me on that, because there's a lot more that goes into a software effort estimation than what I just said. So, talked a little bit about this concept. In general, my experience, I've been doing this for a couple of years now, regression is a common technique for us to create cost/effort estimation algorithms. And it continues to be popular, and the things that we like about it are it's based on statistics, and we're all comfortable with statistics. It's easy to see that effort equals A plus B times size to the C. It's easy to, there is, at the end of a regression, there is an equation, and the equation has, it's got its t-tests and its p-values and things like that. It's r squared. We're comfortable with it. With regression, it is often acceptable for us to test the results against the entire data set, especially because software effort data sets are often kind of small. With machine learning, since the algorithm learns from the data, it's really always wise and highly recommended to have a training set, the set from which the machine will learn from, to create an algorithm or a classification. And then the data set, the part of the data set gets held out to determine how well the algorithm performs on the data not in the training set. And in cases where you have a very large set of data, 75% for training, 25% for testing, it's a good rule of thumb. If it's not large, there are techniques. There's techniques like bagging and bootstrapping that they allow for multiple samples of data, not necessarily unique, but randomly selected, to represent a training sample, and then there's an aggregation of the result. So instead of taking 75% out and saving 25%, you use 75%, different 75% multiple times, and that's a simplification of both of those techniques. But the idea is you do multiple iterations on creating a model and aggregate the model. So now I'm going to talk about, that was not a very good transition, sorry, a couple specific machine learning methodologies. And no one is going to leave this presentation being an expert on any of them, because 45 minutes is not enough time to, even an hour is not enough time to go into a whole lot of detail. But I'm going to talk about random forest. It's an ensemble technique. So an ensemble technique means that instead of building a model once, a model is built multiple times, and then a aggregation, whether it's averaging or voting, an aggregation technique is used to determine the best prediction based on the n models. So random forest, instead of having one decision tree, there are n decision trees. So the training set is bootstrapped many times. So a random process is determined to figure out what the training set is to create decision tree one, a different training set that might contain some of the elements from decision tree one, but will also contain elements not from decision tree one. So a tree is completed using each of the bootstrapped examples, and then whichever ones weren't selected become the test set. And then an average prediction is based on the result of all the trees. So simplification, it's way more complicated than that. I can provide anyone who's interested in lots of documentation about that. Another technique that has seen success in the literature, and I am presenting 4 techniques that have seen success in literature with software estimation studies. Just there are many other techniques, but and time constraint. So support vector machines. It's used for both classification and regression. So it looks at instances from 2 different classes and creates a hyperplane that tries to maximize the margin. So if you look at the picture, the support vectors, which the support vectors are the 2 vectors that contain the samples closest to the hyperplane. They represent the cases on the borders. The number of support vectors that one can create represents the complexity of the model. This is a very simplistic one because 3 dimensions is more than I can handle in this little picture here. So these machines or models are good for handling, a lot of noisy data with a lot of outliers, and also good for handling a large amount of data sets, or a data set with a large amount of examples or rows. Okay, linear regression. This is a machine learning technique. It's not a modern machine learning technique, but it has a long history, many domains. Statistics, economics, cost estimating, psychology, political science, social sciences. It works by figuring out how close each point comes to what's the best line that has the smallest distance overall for all of the points. It doesn't work on qualitative data. So if one is using linear regression to solve a software effort estimation problem, and they have qualitative data such as the type of application, or whether it's air, space, land, auto, there needs to be some sort of a binary encoding or other transformation to turn qualitative data into quantitative data. But it is very popular, certainly in my world these days. And then the final one I want to talk about, and this is not comprehensive, there are a ton more machine learning methodologies that you might be interested in if you're interested in machine learning. So KNearest Neighbor. It's a supervised machine learning algorithm. It can be used for both classification and regression. K is an input to the model, and it indicates the number of neighbors the algorithm should consider to figure out the answer. So it's building clusters, And if you think about memorization, if you remember what the answer should be when the question has certain characteristics, that's what tells the algorithm where to put each of the data points. So if you're looking at this picture and there's 3 clusters, and each of those clusters has a centroid, and it, based on the centroids, it figures out which elements are closest to that centroid. And it uses Euclidean distance, which is a straight line between 2 points, to compute the distance between points to determine which cluster, based on the centroids and the other data points, which cluster is the best place to put each data point. And so it supports classification. It also supports regression problems through classification. So that was my spiel on machine learning. I want to talk a little bit about the experiment that I did. And I already mentioned the results were pretty disappointing. I made a decision that I was going to pick a data set, publicly available, and determine how to filter that data set and then I was going to try it on multiple machine learning algorithms. And I picked the data set and determined that I was going to be unflinching on changing that data set to make my results look good. So my results don't look all that good, but I think I learned a lot. I learned how best to use those 4 machine learning methodologies that I talked about, and I learned about I learned things that I probably should have done going forward. So the data set came from the ISBSG database, and I filtered it. I looked at count approach being either IFPUG or NESMA, because they're very similar. Functional size needed to be greater than 0. Work effort needed to be greater than 0. I needed to have a year of project. I worked only with enhancement projects, and I filtered out anything that didn't have a quality of A or B. So my data set had 4,448 examples, rows, with 9 columns that I included, features that I included in the analysis, except there were some exceptions. Some of the algorithms that I applied didn't tolerate missing data, and some of them didn't tolerate non-numerical data. Excuse me. So I had to sometimes make some adaptations for that. So I did linear regression, random forest, support vector machines, and KNearest Neighbor. And I used the RapidMiner tool for the experiment. So what's really cool about this tool, especially for an experiment where you're trying to do comparisons amongst different methodologies, is if you look, and I actually have a slide that tells you what all these operators do, but I could set up, and I set up this scenario, and if the things you want to notice, all of the things starting from the left up until this item that's called cross-validation are all just setting up the experiment. And I actually did the analysis twice. I did it once using the cross-validation, which allows me to get performance characteristics out of the model. And then I did a data split, where it says split data, that allowed me to feed 75% of my data sample to the model, and then apply model takes the model that comes out of the random forest model and takes the other 25% of the data and just writes it into a CSV or an Excel file so that I can do my own analysis as well as looking at the performance statistics that come out of the cross-validation. So that's, I ran it twice, and I ran it, the cross-validation, I think I have so the cross-validation is it's a process that has sub-processes. So in the same breath, the random forest operator here has exactly the same parameters as the random forest operator here. So I'm running the analysis twice, once to get RapidMiner's opinion of how well the analysis was, and once to be able to do, I did the RMME and the PRED 30 and PRED 50 just from the Excel file. So I wanted to look at it from multiple perspectives. So if one wants to look back at this for a second, just, get the results from the file that has the 2020 icebags data set. And the select attribute operator is going to eliminate features from the study that are irrelevant or mostly missing values, which anyone who's had experience with the icebags database, it's a quality database, but it has probably 300 features. And most people fill in 10 or 15 of them. So, and then I added filters to, create the filters I already mentioned. The cross-validation, it runs the random forest algorithm through a performance operator. And what I started to say and distracted myself. What's cool about this RapidMiner is that I set this up once, and I did have to make some variations, but I was able to do effectively the same test for all 4 methods that I mentioned by just replacing the random forest in the cross-validation subprocess and in the random forest process that went to the apply model. And as I said, there's some variations because linear regression doesn't take qualitative parameters, so I had to turn them from nominal to numeric, stuff like that. The split data funnel 75% into the actual random forest operator for training and 25% into the applied model operator for testing. I already talked about this. So my results were pretty bad. I think that going forward, and I would really, I'm not going to lie, I'm a little bit of a nerd, in case you haven't already figured that out. And it was really fun for me because I was trying to learn about specific machine learning techniques and how we might be able to use them in my business to improve software estimating technology in general. And I did learn a lot. I think that my steadfast decision not to change my data set after I started to do analysis was maybe a little stubborn, but I wanted to see how the different methodologies paired up against each other, and they all did equally. I mean, random forest, I think, did better than the others. And random forest being an ensemble model where you don't solve the problem once, you solve the problem 100 times. You build 100 trees and take an average. You take advantage of the wisdom of crowds, which is well documented to be a smart thing to do. So, but in general, they all did pretty poorly. But I am going to do more studies, and I'm going to do more focused studies, maybe on a specific industry. I did not leave out industries. I took it across industries, which is probably a bad idea. I took it across application types, which might also have been a bad idea. But it was a fun learning experience, and I think I know a lot more about machine learning than I did, and I know what my next steps are. So machine learning, it's here to stay. Technology is in the right place. Big data, we all know how much Facebook knows about what furniture we buy and where we get wedding dresses or dresses for our son's wedding and things like that. Applications in software estimation are burgeoning. It's maybe a little aggressive, but I think there are applications there, and I think that we have enough data that we might be able to harness to create some good machine learning solutions to help us. And even if they're not the solutions that we present to the consumers of our estimate, but maybe they're the solutions that we present to ourselves to increase confidence in our estimates that we present to our consumers. There's the black box issues. They continue to hinder, certainly in estimation projects, because consumers of my estimates want to know, well, what's the equation? And sometimes you can't do that. I have 100 decision trees. I've averaged all the answers, and they're not easy to present sometimes. And I talked about the bad results here, but I think more refined data studies with maybe specific application groups and business types, and I think research into better ways to make the results more visible in a meaningful way, not to say that we should stop presenting results that come out of a machine learning application like RapidMiner, because there are, and I worked with one particular performance operator, but there's multiple performance operators that could be used to evaluate a model to give confidence in it, even if there isn't an equation, but rather a conglomeration of trees or equations. I believe this is my last slide, since it's labeled wrap up. And I am ready. I'm going to turn this back over to Susan, but I am ready to entertain any questions that anyone might have.
Adequate data for training/validations is one of the biggest impediments to machine learning. We simply don't have enough most of the time. You mentioned a few techniques to mitigate this to some extent: cross-validation, bootstrapping, etc. How do you feel about data augmentation methods like SMOTE to create synthetic data points to artificially boost your data sets?
I'm not sure what SMOT stands for. I worry about data augmentation. Not to say that I haven't done it, because sometimes you have to, but I think it should be done carefully, and I think it should be well documented, and I think the consumer of the estimate should be made aware of how much of the data was for real and how much of the data was synthetic. Feel free to email me.
Arlene, thank you so much for presenting with us. We always appreciate it.
My pleasure.